Hello everyone, welcome to this video. In this video, we'll be starting with another topic which is group isomorphism. So let's first of all in this video see the motivation for group isomorphism, what actually it represents and why we are studying this group isomorphisms. So you see, let's moving on to isomorphisms, let's first understand this thing through some questions. That the first question that I am posing to you is, are the two persons doing the same thing? The one person is counting like this 1 2 3 4 5 6 and so on, right? The second person that is also counting, but that is counting in the way that that person is counting like 1 2 3 4 5 6 and so on, right? So both of the persons, are they doing the same thing? The answer is obviously yes, they are counting, right? But one of them is counting the things in English and another one is counting the things in Hindi, right? So both are counting the objects, but they are using different terminology to do that, right? For the next example, let's see, are the two things different? One person says 2 plus 3 is 5. Another person says 2 जोड़ 3 5 है, right? They are basically saying the same things, right? But their terminology is again different. So two persons, they are in agreement on some concept. That means they are saying 2 plus 3 is always equal to 5. This person is also saying the same thing, this is also saying the same thing, but their way of saying is different, right? So two persons, they are in agreement on some concept they are describing, but they are using different terminology to describe that concept. So is this thing clear to all of us? Okay. So similar situation also arises with groups. The same group is described with different terminology. So as for an example, we have studied about dihedral groups, right? So within a dihedral group, we saw that the dihedral group, which is basically the symmetries of square, it could be expressed in geometric terms, like we could express its rotations via r0, no rotation at all, r90, anti-clockwise rotation by 90 degrees, r180, anti-clockwise rotation by 180 degree, r270, anti-clockwise rotation by 270 degree. Then we have reflections, which is about the horizontal axis, reflection about vertical axis, reflection about the main diagonal, reflection about the other diagonal. So these 8 elements form the elements of this group D4 under the function of composition, right? So this represents rotation group of symmetries of square, which we usually denote by D4, right? This is one terminology to define the dihedral group. We also saw we can define this dihedral group by the way of permutations. If you remember, we have described this symmetry of square by marking the given square whose 4 corners are marked by 1 2 3 4. Then we may define the rotations like this: 1 go to 2, 2 go to 3, 3 goes to 4, 4 goes to 1, and so on, right? So for this, all the elements, they are represented by these 8 elements: E, then rho square, rho cube, then sigma rho square, and sigma rho cube, right? Where what is sigma? Sigma is defined by this permutation here: 1 goes to 2, 2 goes to 3, 3 goes to 4, 4 goes to 1. So this corresponds to rotation, right? And we have this phi here, or basically this you can call this to be rho, because we are using the notation rho here. So rho here is described like this: 1 goes to 2, 2 goes to 1, 3 goes to 4, 4 goes to 3. So this is basically the reflection, right? So these two operations together form whole of the group D4. So in both the cases, we are defining the dihedral group, where it represents the symmetries of a square. However, the terminology in both the groups is different, right? So in both the groups, we are defining the symmetries of square. For another example, we have a cyclic group which is having order n. It is generated by A, right? The same cycle, so it would have because it has order n, so it would have at most n elements within it, and after that the elements would repeat, because we have a cyclic group, and the elements of cyclic group, they repeat after some time. So this group is similar to the group which is this is similar to the group of integers mod n, because here also the order of the group is equal to n, and after n the elements repeat themselves, so they also act as a cyclic group. So here the operations, they are performed in this manner, that when we take a to the power r, a to the power s. Why this is so? Why they two are similar to each other? It is because in cyclic group we have all the elements having of this kind, a to the power something, say a to the power k. So if we multiply two elements of such kind, say a to the power r into a to the power s, what we are eventually doing, we are getting back another element which is a to the power k, where this k, how it is obtained in usual sense, in normal sense, it is just r plus s, right? That is equal to k. However, now we are doing a mod n to it. Why? Because we have finite elements present within our groups, and we have only n such elements, so therefore we are taking mod n. So this operation is similar to that which we perform in the group of integers under modulo n. So this group Zn and this group cyclic group having order n generated by a, they are similar to each other, right? So you see, when so now notice here that what we are saying, when two groups, they are defined in different terms, so we have two groups and we are defining the two groups in different terms, and those two groups, they behave similarly, right? So if that is the case, we say that there is an isomorphism which is present between the two groups. So you should note this word and keep this word in your mind. What is isomorphism? So we have one group here, we have another group here, they represent the same thing, they are basically the same thing, but we are using different notations, different notation here and different notation here in order to define these two groups, right? So this is the idea of isomorphism. So I hope you understood this concept well. Well, that is it for this video. Thank you for watching.